So to give ourselves a little bit of a running start in terms of our posets and jumping into lattices, here's our reminder of the definition of what a poset is. A poset is a set in combination with a specific type of relation. The type of relation we care about is something called a partial order. And it's called that because it basically allows you to, and it's the same term, order all of your elements in your set. In other words, you can see how they're related to everybody else. Again, I realize both order and related are bad words to use when you're dealing with a relation, which is a partial order, but unfortunately they're the same names. So your relation here, it's partial order, it's got to be reflexive, anti-symmetric, and transitive. So you're looking at those three properties define your partial order. It's totally fine if the relation has some of your other of our 6 properties, but it's got to have those 3. And then the partial order is, like what we just said, your set in conjunction with that actual partial order, and that's your poset. One of the big things that we deal with posets is we look at the picture of the poset, and these guys are called Hosta Diagram. All right, why are we not moving? Just a second. Awkward. There we go. Is the Hosta diagram, which roughly speaking is similar to the digraphs we had before, or technically speaking those directed multigraphs, which I've just been calling digraphs. Our Hosta diagram doesn't have all of the extra stuff that a digraph would have. So it doesn't have the loops that we would naturally get by the partial order being reflexive. It reorders your vertices so that all of your little arrows, all your little directed edges are pointing in an upwards direction. They don't have to be vertical arrows, but they're at least pointed in an upwards direction. So you're always traveling up from bottom to top of your Hosta diagram. We remove all of our extra edges, those things we've been calling transitive edges, the red arrow in the little diagram. And then once everything's pointed up and the extra stuff is removed, we then change out the arrows to edges. Okay? So that's the snapshot of where we've been. Here's the new stuff. Definition of a lattice says you are a poset. Typically people label it L for lattice. Where, so that means your poset, you've got your set of all of your elements, you've got your partial order. Where if you pull any 2 vertices, any 2 points in your Hosta diagram, or in context of how it's written here, any 2 elements from your set, those guys are always going to have something called a meet, and they're always going to have something called a join. Now, we haven't defined what a meet and a join are, and we're going to do that in just a second. Okay? So let's start off with a meet because I wrote it first in the definition of a lattice. A meet is actually an operation, like addition or multiplication or union or intersection. It's an operation on 2 elements from your poset, or if you prefer, 2 vertices from your poset, where you're looking at your vertices when you're in your Hosta diagram. So officially speaking, your meet is defined as the greatest lower bound. That's a very, very technical thing in math. Here's what it actually means. Before we get into what it actually means, the symbol here for a meet looks like that little caret symbol. Okay. So what the greatest lower bound means is your meet is going to be related to your element A, and it's also going to be related to your element B. So in the Hosta diagram, it has to be lower than both the elements A and the elements B. All that gives you is lower bound. So lower bound here is just lower, tells you that it's below in the A and the B in the Hosta diagram. Now the greatest lower bound means you've gone as high as you possibly can in the Hosta diagram, or in layman's terms, it's the biggest guy that's below the A and the B. So here's what it means technically. There's no vertex C, or there's no element in your poset where the meet of A and B is related to C and C is related to A. Notice what this would mean. This would mean you have at least some sort of little path from the meet up to A. Okay? That part here is not a problem. The problem is the fact that you have that same chain, or almost that same chain here, that path, going from your meet to B. So here you also, the meet is related to C, and then C is related to B. So notice what this would mean. This tells you actually that that element C is related to both A and B, but it's bigger here than this guy, the meet of AB. Okay? So this element C doesn't exist if it's different than the meet, okay? Because the meet's supposed to be that biggest one. Okay? So in terms of a picture, here's what you would typically see. You'd see in the Hosta diagram your element A and B. You go down from your elements A and B, and the first one in common that's below these two guys, that would be your meet. Okay? Now we're going to see a bunch of examples later on today, and the meet doesn't always look in this exact orientation. If these two guys are at different levels, maybe you have to go further down from the one that's at the higher level to get to the meet and stuff like that. But this here is sort of the classic picture that people think of in terms of, hey, how would the meet look like inside of your actual Hosta diagram? Okay. Now, that's what a meet is. The lattice has to have every two elements in the lattice have both a meet and a join. So let's look at what a join is next. And it turns out a join is essentially the exact opposite. So the official definition of a join with, well, that is super duper awkward. It looks like I could do a typo here. Anybody spot what the typo is? So I'll read through it and see if you can spot what the typo is. So a join is defined as the least upper bound of the two elements. That's correct. There's no typo there. Okay? So the least upper bound means what? It means your join is going to be above your two elements A and B. And the least upper bound, so the upper part says it's above. The least upper bound means it's the first one that you come to in common between the two elements A and B. Okay? Now, if you spotted what the typo is, awesome, it's totally with this symbol. This is the correct symbol where your join looks like a capital letter V. It's not really a V, it's like an upside down caret. But notice here in terms of the two symbols, they look really, really similar. I'm not going to lie, when I first learned these, I would flip-flop them all the time. But one way to remember them is that little guy that kind of looks like an arrowhead is always pointing in the direction of where your A and your B live in your Hosta diagram. Yeah, so the typo is totally in the symbol, and it's the symbol right here for join. So let me go ahead and erase that. I love the fact that I can actually erase it in a somewhat non-crazy way. And I don't know what I was thinking. I literally did the symbol for meet all the way through this. I suspect maybe I just copied and pasted. So the join, the symbol's flipped. It looks like a capital V all the way through. Okay. So notice here, least upper bound. So this first one you get to as you go travel up the Hosta diagram. This says that both A and B are related to the join. And here's the condition that you can't have. You can't have somebody between A and the join, between B and the join, that's in common. The main thing here in both of these two definitions is the fact that this little element C isn't allowed to be between either your meet or your join and your AB elements if it's common to both of those two paths. It's totally fine for both your meets and your joins to have to be on longer than a length one path between it and either your A and your B element. The main thing is the meet and the join are the first elements in common to your two vertices A and B, or your two elements A and B from your poset, either going up the Hosta diagram or going down the Hosta diagram. Okay. So that's the idea behind these meets and joins. So now that we have that typo fixed, let's look at some examples. And I've got a bunch of different examples prepped up. Actually, almost exclusively the rest of today is actually some examples to look over. Got, I think, one more definition and one more fact, and the rest of it's examples for today. But what we'll start with is we'll start by looking at examples that are just the Hosta diagrams. Okay? And I've got several of them prepped out for us. So suppose we look at these first guys, and I went ahead and prepped out. I actually have a grand total of 5. You can see 3 of them right now. So here, the question is, where the setup is, we've got some Hosta diagrams that are given. We're not told what the actual post set is, what the actual partial order is. We're just given the Hosta diagram. And from that information, what we want to know is the underlying post set, is this guy a lattice or not? Well, remember what the definition of a lattice was. You had to have every single pair of elements in your post set or every pair of vertices in your Hosta diagram. It's not really an either or. That's 2 different ways of saying the same thing. Those pairs of elements all have to have your meet and your joins. So I personally think it's often easier to do this inside the Hosta diagram, which is where we're going to start. But we also have 2 really common types of post sets that we've looked at in the past. And those guys, because we have the formula for the partial order, we'll look at them a little bit differently. But we'll do those next. So right now. So say we look at this first guy, and we've talked about somebody that looks like him before. We said this guy actually has a name. It's called a chain. We've got 4 elements or 4 vertices in the chain, and in the Hosta diagram, the picture here, we have 3 edges. Okay? So if we looked at every pair of elements, automatically, if you pick 2 elements that are the same, and this is why the definition is talking about a subset, if you pick these 2 pairs of elements to be the same element from your set L, what happens? It's not really a cardinality 2 subset. It's just the 1 element. Technically speaking, you can still apply a meet and a join to 2 guys where there's the same element. You don't normally, but technically it is defined. And in that case, if you have the meet of A and A, it's still A. If you have the join of A and A, it's still A. Okay? So what we're going to look is we're going to look at properly 2 different pairs of guys. So if we look at this first example with a chain, we have 4 elements, and if we want to pick out 2 of them, 2 different elements, this is the same thing as saying I got 4 elements and I need to randomly choose 2 of them, 2 different ones. So this is the same thing as 4 choose 2, or there should be 6 cases. Okay? So maybe we look at something like A, and we look at, oh, I don't know, maybe we look at the meets first. So we look at A, and maybe we're lazy and do B. So that would be these 2 guys. Anybody have a guess what the meet of A and B might be? And I'll go ahead and highlight them in the picture. And while you guys are thinking out what the meet of A and B would be, I'm going to write out the next ones we'll look at. Or the next 3 we'll look at. Anybody have a guess? Remember, the meet was the greatest lower bound. Ooh, this one here is actually a trick question, slightly. The meet here is A. So you're only looking at elements that are below A and B, except here's where that trick comes in. The trick is it's okay to look at your element too. So this is the special case where you actually have, if you're looking at this part right here, notice in and of itself, it looks like a little baby chain where you've got 1 edge and 2 vertices. Huh? In that case, the meet, the greatest lower bound, well, if we look at A is somebody who's definitely below B. No worries there. Technically, A isn't strictly below A itself, but in terms of the meet, in terms of this notion of a greatest lower bound, the definition was actually in terms of the relation. You had to find somebody that was related to A and somebody that was related to B, and it turns out A is related both to itself and to B. So that's actually a special case where you actually get 1 of your 2 elements. So perhaps a bad one to start off with. I probably should have started off with that second one there. Okay. Now, that being said, anybody have a guess what the meet would be between A and C? Oh, let me highlight it. That might help. Oh no! I'm not sure if I can unhighlight. Let's try it. Oh, that definitely did not work out as awesomely as planned. If we're looking at A and C, that one and that one, it is not B. And here's actually why. B is not related to A because B is above A. So meet is somebody that has to be related to both A and B. And then once you find somebody who's related to both, I should say B, A and C in this case, and once you find somebody who's related to both A and C, then you find the biggest one. So in our case, remember in Hosta diagrams, somebody who's related to somebody else is, you look down. Yep. So in this particular case, what happens? We're going to go ahead and we're going to see, just find it. It will still be, it'll still be A again. Anybody have a guess on what the meat of A and D would be? Don't overthink it. So while you guys are thinking, I'm going to re-highlight. And yep, it would be A again. Now, there are actually 3 other pairs, and for these 3 other pairs, instead of listing them out, because I definitely didn't give myself enough space right here, actually, if I blow it up a little bit, we'll have more space. Yeah, no, not really. Oh, well. All right. The other pairs are going to be what? They are going to be the races. They would be, if you look at B and C, and if you look at B and C, notice the meat of that guy is going to be the lower one. It would be the B. You could also look at B and D. And in that case, again, it's just a subchain or part of the total chain. It looks like just a single path. So the meat would again be the lowest guy. In this case, it would be B. And if we look at the 6th and the last possibility, what would happen? We'd be looking at the meat of C and D. And in this case, it would be the C, the lowest one. Okay? So what does that mean? Even though we didn't explicitly write out those last 3 guys, those last 3 pairs, in each case we were able to find the meat, no problem. Are you guys okay if I don't write out all of those last 3 pairs? Or do you want me to try to fit them in right here? All right, seeing no responses, I'm going to go ahead and then look at the other thing we need to worry about. So far, this chain has totally got all of its meats. We wrote out 3 of them, and then we talked out the other 3. So the other thing we have to worry about is we have to worry about the joins. So if we look at the joins, and I'll on purpose grab those other 3 pairs that we had, the pattern for the joins was B, and then the join symbol, and then C. Okay? So here, the other 3 pairs were BC, were BD, and lastly were CD. Okay? Now, if we looked for the joins of these guys, and let's go ahead and pick on BD first. I realize that in no way, shape, or form does it make sense to do that one, except for the fact that I on purpose wanted to make it longer than just one edge between them. That was the only reason I picked that one. So if we look at the 2 vertices, B and D, anybody have a guess who the join might be for this one? And remember, the join is the least upper bound. So this is somebody that both your 2 elements need to be related to. So it's got to be somebody where you're looking up the Hosta diagram. And you've only got 4 choices, A, B, C, or D. In terms of what you typed, no, but in terms of what we just talked through, yes. So if we look at B and D, the join of this would be D, the top one up there. Why? Because B is related to D according to these edges, and D is related to itself, and there's nobody that you could pick lower in the Hosta diagram that would still work. Now, if we went and looked not at B and D, if we looked at B and C, using the same logic, what would be the join here? We said previously the meet would be B, the lowest one, but in terms of the join, this is the least upper bound, so you go up in the Hosta diagram. Right, so the key thing is, and this is the trick with chains, is you have to remember that the relation is actually reflexive, so you're always related to yourself as well. Now, we don't always use it, and in fact, other than dealing with two elements that are related by way of some chain, you won't use it for the meets and joins. So this first one is kind of a special case. In this case, the join would be C, the top one. It is difficult to write with highlighter, so let's try that again. Now, if we look at this last one that hasn't been filled in yet, this join of C and D, any guesses what the join of C and D is? Don't overthink it. Now remember, the meet is the greatest lower bound, so that will be C. But the join is a least upper bound. So a least upper bound for a join means you're always looking up. So we need somebody that's related to both C and to D. Well, the only guy related to D is D. So then you check and say, all right, well, is C related to who? Well, C is related to itself, so C, and C is related to D. So then you look to see, all right, well, what's the common one that they're both related to? So anybody have a guess what the common one that they're both related to is? So from our analysis, the answer will either be C or D. And so far, I had one vote for each, and now I've got a couple other votes for D. So yes, it does turn out to be D in this case. Key thing with the joins, you're always looking up. And here's the takeaway for this one. If you have two elements, so this is an aside. Let me actually put it in different color. If you have two elements here, A and B, it turns out your meet is of the two elements of your chain is always the bottom one, and the join is always the top one. If you have actually any length chain and you're pulling the ends of that chain. Notice any two elements we pick here is always going to form some subchain of the coset. So your meet is always going to be the lowest element of the two, and the join here was always the top element of those two. Now, that's only true with chains. So we have to do a slightly different analysis if we're dealing with other things. And to go ahead and complete this, if we looked at A join B where the symbol's flipped, A join B here would be the top one would be B. A join C, so the symbol flipped, the top one would be C. And A join D, the top one would be D, so those two would also flip. That's a chain. Now, one of the reasons that I went ahead and put the chain first is, one, the poset's relatively simple, but two, if you can spot a chain inside of one of your other posets, it makes finding your meet and your joins easier. So chain is the first thing you look for. The other thing you look for inside of your arbitrary poset would actually be this second figure. So for this second figure right here, it also has 4 vertices. So there's 6 possibilities that you can pull when you're looking at your ordered pairs. So here I'm going to attempt to be slightly strategic, and we'll write the things down over here side to side. Okay? So if we look at meets first, we could have A meet B. We could have A meet C. We could have A meet D. We could also have B meet D, or C meet D. Oh, and B meet C. I knew I was missing one and I just didn't spot it. All right, so let's see if we can't find these guys. So if we look at A and B and we look for their meet, notice the relationship between A and B, the substructure, or if you will, the sub-poset, not that it's ever called that, but only this part of the poset that is dealing with the connections between A and B. This guy right here is just a tiny little chain, and we could actually use the same logic that we had previously. So if we're looking at the meet, we'll look at the bottom one, and that would simply be A. Using that same logic, anybody have a guess who the meet is between A and C? It would be A in this case. Now, if we look at the meet between A and D, that's not just one little thing. You actually have to go up A, B, D, or totally fine to look at as A, C, D. In either case, you now have a length 2 chain, or a length 2 path if you prefer. So any guesses what the meet would be between D and A? Don't overthink it. Well, the meet is the greatest lower bound, so it's got to be somebody that's related to both of them. And yeah, because A here is the bottom element, or your least element for this poset, you're going to have A going on, or A to be your meet. So we'll write that down. Now the next two guys, B and D and C and D, when you look at their relation or how they're oriented in the actual poset or in the Hosta diagram, notice they again look like a little chain. So we know that from little chains, you always take the bottom one for your meet. So the bottom two would be respectively B and C. So now the only one that's slightly complicated, okay? There were two in here that actually were slightly complicated. The first one was that one, and the second one is this guy. So if we look at B and C, we want to try to find the meet of B and C. In other words, the greatest lower bound, excuse me. I knew I messed up the ending there. All right, so what do you need? You need somebody who's related both to B and C and the biggest one. So who is an element that is related to both B and to C? And you don't have a lot of options here. And if you're related to somebody in the Hosta diagram, you're below them. And everybody's related to themselves. Hint, the answer's not going to be D. So your only three options are A, B, or C. I've got a couple guesses coming in. So far, all of them are correct. So it turns out in this situation, there's only one element that's below B and C. It's A. A is related to both B and C. The answer here is A. This picture right here is quintessentially the picture that you think of in terms of meets and joins, where the meet of B and C is this guy right down here, A. So I'm going to go ahead and label it in the picture. Now, we've got all of our meets defined. So this guy here, in order to be a lattice, we need to check to see if all of the joins are defined. I am not right now. I have one prepped up and it looks like it's just not displaying. So we'll go ahead and check to get that displayed. That way you guys can look at it a little bit before we're there, because we're not actually to that example yet. All right, you should have a poll displaying, but this is going to be like probably the last example we get to today. All right, so for this guy here, next thing to do is to look at all of our joins. So if we look at all of our joins, we have all of the same guys, except now we're going to flip-flop the symbol. So we've got A join B, we've got A join C. Both of those guys we already said were little tiny chains in and of themselves, so we know it's going to be the top element, the B and the C this time. We also have A join D, so we'll look at A and D again. I'm putting them in the same order as before. This one here is the one that actually is slightly interesting, so we'll come back to it. And then the last three that we have are B join D, C join D. Again, these guys are not super interesting because B and D and C and D form these two little length 1 chains. So both of them would grab our top element for the join. And the last guy is, again, one of the interesting ones in this particular example. It is dealing with, I wrote down the wrong thing, B and C, or the join of B and C. So let's look at those two guys specifically. So if we look at A and D, A is the bottom one, D is the top one. Any guesses who the join would be? And remember, the join is somebody that both A and D are related to. So it's got to be somebody that is above both A and D. In this case, we had a length 2 path connecting them, so you just grab the top one. That's actually the same situation as those other 4 I filled in for us. Now, last one. This one is the only one that's slightly more than vaguely interesting, which is looking at the join of B and C. So if we look at B and C, which are on the same level of the poset, the join is somebody who both A and C are going to be related to. So again, you're looking up the Hosta diagram because this is going to be the least upper bound. So any guesses what the join of B and C are? Don't overthink it. We've got B and C. Yep, it will be D again. So let me write that actually in the picture. This would be the join of B and C. Now, these two pictures, the one for the original chain over here, and then here's the small picture for it. And then this guy here that looks sort of like a diamond shape or a square shape. These two are your quintessential things you look for in your larger posets. Okay? If you've got your elements stacked on either end of a chain, your join's the top end, your meat's the bottom end. If you have two guys that are roughly speaking at the same level, so they're not forming a chain between them, you look up until you find your join, you look down and you find your meat. So you're typically going to have some sort of diamond-esque shape. And depending on what actual edges you have in there, it may actually have some extra edges in there, but it should look like some sort of polygon-esque shape if you looked at the whole thing together with the meat and the join. Now, analysis. Answer for these two things. So on the example that we just did, we were able to find all the meats and all the joins of our poset. So that means this guy is a lattice. That's the conclusion. Now, I forgot to write the conclusion of what we wanted to get to for the first one for the chain. What do you guys think? Was that first chain a lattice? Did we have all of our meats and our joins? The answer is either yes or no. So what do you think? Is a lattice, is not a lattice for the first one? Definition of a lattice was you have all of your meats and joins defined. In other words, you can find them in the poset. Hopefully you're thinking back to that first example, which is even though we didn't write out all the meats and joins, we only wrote out half of them. We actually did go and talk about the other half and define them. We found them. So that means this guy is also a lattice. So moving on to the next example. Our next example here, we want to see if this guy is a lattice. And I'll go ahead and write out, I really don't want to write out all of them. We'll write out some of them. Okay, we'll write out some of the important ones. Okay? And then when they start duplicating each other, we'll stop writing out some of those other ones. Or maybe we'll write out all of them. All right, so if we want to look forward to see if all of our meats and joins exist, what happens? If we start off with our meats, we can look at A. And A, you can go A to B. You could go A to D. you could go A to F. So all three of those guys, I just walked up this left-hand side. Okay? So A to B, that's somebody that looks like a little chain. A to D, also somebody that looks like a little chain. A to F, also somebody that looks like a little chain. And with a chain, the meat is always the bottommost element. So in all of these cases, A. And you could do the exact same thing right over here on the other side. We could say, hey, A meet with C, A meet with E. Again, you're going to form chains, and the lowermost one is A. Starts getting interesting when you're not just dealing with A. Okay? So here, suppose you start with B. Okay? So with B, you could say, hey, B, that's not a B. You could have B meet with C. You could have, so there's a slightly interesting one, because does not form a chain. Now B and E forms a chain. B and D forms a chain, so we know both the meet and the join would be just fine. B to F forms a chain, so the meet here would still be B. And that takes care of all of those cases. So I'm just going to write down the B to C one because that one's the one that's the interesting one. Now, if we look at B and C, anybody have a guess on what the meet is of B and C? Remember, meet is from the bottom. So it's the greatest lower bound. So you go down. E would be the join. Yep. So if you go down, greatest lower bound, that would be your A right here. Notice how you got an overabundance of A's here for your answer for your meet. That is not unexpected. You have a tendency to have the lower part of the poset be where all of your meets come from, and the upper part of the poset be all the elements where your joins are coming from. All right. And we talked out the other B ones, so I'm not going to write it out. So what happens if you start with C? Well, the exact same thing. You could have B and C, which we already dealt with, B and D, which is a little chain, B and F, which is a little, not B, C and E, which is a little chain, and C and F, which is also a little chain. So I'm not going to write out the ones with C. But what happens if you start with D? Well, with D, there's two guys that you can look at that we haven't talked about before. You could look at D, and everybody below him we've actually would have dealt with, either written out or talked about so far. So we can look at either D and F or D and E. Well, D and F is a little chain, so that one works just fine. The meet would be D. So let's look at D and E. Remember, the meet is below the two elements. So we're looking for somebody who's related to both D and E. So that's going to be either themselves or below, and it's got to be somebody that works for both of them. So any guesses? I'm going to highlight these two elements. So your options here are A, B, or C, because, ooh, there's a guess. There's a guess here that there's no meet going on. And that is actually the correct answer. Here's why. If you're trying to find your meet, there are three elements that are related to both D and E, and then you try to find the biggest one. And it turns out you have two candidates. Okay? You have candidate either B or candidate C, and the fact that you have two candidates means the meet is not defined because there is no greatest or biggest lower bound. You just have a collection of them. So this one here is actually A, does not exist, and that is because you could pick either B or C, and you don't know which one to pick, basically. Now, analysis. What does that mean in terms of us trying to figure out if this guy is a lattice? What do you guys think? Could this poset be a lattice? Correct. So because you have one of your meets undefined, this guy is not a lattice. And that actually is how you determine if somebody is not a lattice. So what you look for is you actually look for things just like this. You look for, hey, I'm trying to find a pair of elements where I can break having the meet or the join. In other words, where I have more than one meet or join. So that's one possibility of where you can not have a lattice. So that takes care of these guys. For the next two examples that I've got, instead of writing out all of the possible meets and joins, let's see if we can't find where bad things could happen. Okay? So you're looking specifically for pairs of elements that do not form little subchains, that don't form little paths. Okay? So like D and E right here, there was no direct path between them. So next two examples before we get into named examples. Suppose we have these guys. Oh, awesome, I put some extra space here. And these are the two examples that don't need the extra space. Oh well. All right, so if we look at these two guys, let's go ahead and look at this one first. So we've got this 1, 2, 3, 4, where is that, 5 vertex example right here. And this guy looks actually pretty similar to the last one, except it doesn't have internal edges in here, right? So if we look at this particular guy, if you pick A and anybody B, C, or E, what happens? You form a little baby chain, and that little baby chain will have both a meet and a join. Okay? If you pick A and either D or E, well, E we already talked about, but if you go on this side, you're also going to form a little baby chain. So no worries there as well. Okay? If you picked E and anybody below him also forms a little baby chain, so no worries there. So the only ones that we're really going to have to figure out is what happens if we pick a pair from B, C, and D. So let's actually write those guys out. So if we look at B and C, well, B and C also forms a little baby chain, so we'll have both a meet and a join. So really, we'll pick either B or C and then D. So maybe we look at meets first. And if we look at the meet first, we'll have B and D and C and D that we want to look at. And we also want to look at their joins. So just to prep up, the only 4 guys that we have that don't form a little baby chain when we look at the 2 elements. All right, so if we look at B and D, the meet is the greatest lower bound, so you look below B and D, and the element shared in common, well, there's only one option. So that guy has to be A. That one is very clearly defined, no worries there. Now, since we're going to look at this pair again, we look at that pair again with the join. Anybody have a guess on what the join would be for B and D? And remember, this is the least upper bound. So you're looking above B and D. Since B and D don't form a little baby chain, there's no direct path between them. That means the only options for the join of B and D are going to be either C or E. You got a 50-50 shot of a blind guess right there. Remember, both B and D have to be related to the join. What do you guys think? Is the join C or E? It would be E, as several people have answered. So if you're going up, notice D is not related to C. So you had to have a join as somebody that is in common, that both B and D are related to it. So the first one that both of them are related to is this guy up here all the way at E. Notice this is one of the pictures that isn't exactly a diamond shape. It's like an adjusted diamond shape. You had an extra vertex over here to get up to that top diamond point. So notice you don't have to just have one edge going up to your join. You might have to travel up more than one edge. Now, if we do the same exact thing with not D and B, but with C and D, so now if we look at C and then D, oh, well, that's awesome that it changed color, but I did not mean for it to change color. Let us undo that then. All right, so we now want to look at C and D and to put back in our previous answers, A and E. All right, so if we look at C and D, if you look at the meet of C and D, any guesses what the meet of C and D would be? Remember, you're going down, so you're looking for the biggest or the greatest lower bound. But this has to be a point or an element of your set that is related to both D, and C. Yep, totally would be A. It's the only one that's related to both of them. Now, using the same logic as before, any guesses what the join of C and D is? Remember, join is where you go up the Hosta diagram. In this case, it would be E, and we said that every other pair of elements you could pick in this post set would form a chain. Chains automatically have both their meets and their joins, so we looked at the only guys that were non-chain oriented, which means our answer here is this guy is or is not a lattice. What do you think? I'll write the word lattice as you guys are thinking. So, is a lattice or is not a lattice? Well, we were able to find all of our meets and joins. Only definition of a lattice is a post set where you have all your meets and joins. So that means this guy must be a lattice. All right, so last one we're going to look at without context. Okay? So suppose you have a Hosta diagram that looks kind of like a Y. Okay? In this particular case, if we want to know whether it is a lattice, we need to figure out if we have all of our meets and joins. And notice, if you looked at A and you picked all of your pairs that went with A, got AB, that's the baby chain, so we've got both the meet and the join. AC, that's the baby chain, so we've got both the meet and the join. AD, that's the baby chain, so we've got both the meet and the join. If we looked at B, we have BC, well, there's a baby chain. BD, there's a baby chain. We're good. If we looked at C and D, well, we already looked at everything that if you had a C and either A or B, so the only thing left that can go with C is the D. So with this guy, that's the only pair that between them you haven't actually formed a chain, which means we need to look at the meet and the join of those two guys. Now, suppose we look at the meet first because, well, let's face it, that's totally what we've been doing so far today. So make sure you actually write a C. That would be so helpful. Our meet, so C meet D is something, and then we'll look at our join as well. So anybody have a guess what the meet of C and D is? Don't overthink it. And remember, for the meet, this is the guy that's related to both C and D. So in the picture, in the Hosta diagram, you're looking for somebody below C and D. Since it didn't form a chain, it's not going to be either C or D, so your only options here are A and E. You want the greatest lowest bounds, the biggest one below C and D that you get that goes directly to C and D, or mostly directly to C and D. Yep, that would be B. Now, the join is where C and D are both related to that element. So this is where you're looking up in the Hosta diagram. Now remember, C and D are both related to themselves, but you have to find one element in your post set that C and D are both related to. So anybody have a guess what it would be? Ooh, I've got a couple of guesses coming in. So far, they are all right. Anybody brave enough to say it to everybody? All right. So it turns out in this case, this is another situation where you actually don't have a join. Okay? So just like before when we didn't have, I don't think we had a meet last time, we didn't have a meet in this other post set up here that had the crisscross edges because there were two options. Well, that's a problem because you don't know which one to pick. In terms of what we have down here, we don't have a join, not because we don't know which one to pick, but because legitimately there is no element that works for both of them. There's no element that C is related to that D is also related to because you don't have anybody above them. This means that because we don't have that join right there, that this guy is not a lattice. Now, this comes to a couple of comments. And specifically, it goes with properties of lattices. in order for you to have all of your meets and joins existing, anybody notice anything that was different about this poset than the other posets? And specifically, it deals with C and D. C and D are what type of elements in your poset? Anybody remember what the buzzword was? Oh, I love some of the answers that are coming in. Some of them are very descriptive. All right, so the thing that we talked about at the end of last time dealt with maximal and minimal elements. So maximal just talked about your top ones. C and D are both maximal elements. It also talked about minimal elements. Those are the bottom ones. And in all of our cases, all of our examples here, A was the minimal element. There was only one of them. But we also talked about a second thing, and we said if you have exactly one maximal element, it's also called the greatest element, or in symbols, one with a little hat. And if you have only one minimal element, then it's called a least element or a zero with a little hat on it. It turns out in order to have all of your meets and joins defined, you can't have the situation where you have more than one maximal element. The same thing happens in the bottom. You can't have more than one minimal element. Why? Because those elements are not comparable. They're not related to each other. So you won't have either your meet or your join. On the top, you won't have your join. If it was on the bottom, you won't have your meet. So what that means is when you look at your lattices, we can actually go back to these 5 pictures and automatically with no work whatsoever, we can say, hey, this guy that looks like a Y, not going to be a lattice. Why? Because it doesn't have a greatest element. It actually has this bifurcation, if you will, these 2 maximal elements. So you need one top element and one bottom element, if you will. And in fact, lattices are so useful, not that we're going to get much into that, but lattices are so useful in the future that when people work with posets, one of the things that they'll do if they have this, they're like, I really need this structure, but I hate this top. They'll actually add in one extra top element, if it happened on the bottom, one extra bottom element, and just take all of these little maximal elements and connect them to that one extra top element, and then bam, they've potentially fixed the problem of it not being a lattice. Okay. So that's some background information, but the takeaway here is make sure you have one top element, one bottom element, and that's sort of a quick check to see if you don't have a lattice. It doesn't guarantee that you still do have a lattice, because notice this picture up here, that was our other example of not a lattice. It had one top element and one bottom element, but with these crisscross things in the middle, that was how you failed to be a lattice. So you can't have too many crisscrossing elements down here, and you have to have one top and one bottom element. That's totally sort of the quick things to look for. All right, so that's it in terms of just the pictures, but let us look at another example of a poset. Okay. So this next example of a poset is somebody called B4. We've dealt with, I don't think we did 4 previously, but we've dealt with these type of guys before, where the actual set is just the power set of 1, 2, 3, and 4, and I really don't want to write all of those down. So we'll write down some of these guys. So this is where you have your empty set, you have your elements 1, 2, 3, 4, you have your 2 element sets, so 1, 2, 1, 3, and so forth. And then all the way up until you get to all 4 of them, so 1, 2, 3, and 4. And in terms of the relations, they're related by way of set inclusion. Now, in terms of building this one, remember how we built this type of poset? You started with cardinality. So if we have cardinality 0, that would be just the empty set. If we have then cardinality 1, and I'm going to do a lazy thing, and this is lazy only so we can make sure to finish off our last example today. Instead of writing all the curly braces, I'm just going to write the numbers. This is actually something people do because they get super lazy. So we've got 1, 2, 3, and 4. Our cardinality 2 ones would be 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. Our cardinality 3 guys would be 1, 2, 3, missing 3, so 1, 2, 4, missing 2, so 1, 3, 4, and missing 1, so 2, 3, 4. And the full set of cardinality 4 would be 1, 2, 3, 4. And when you go ahead and link these guys by way of subsets, notice what happens. We do have a top element and a bottom element. They connect to the one lower and one upper level. And the middle ones connect in the following way. Match where the 1s go, where the 2s go, the 3s go, the 4s go, and there's going to be tons of crossing lines. I'm definitely regretting prepping out with a 4. And when you grab 4, this would be 4, 4, 4. I'm missing a line. There it is, 2 forgot. And the same sort of cross-hatching goes between the level that we haven't done yet. 1, 2 goes to 1, 2, and 3 of them. I lied, not the last one. Make sure I didn't miss anybody. 1, 3. Where'd 1, 3 go? 1, 3, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. And that would, roughly speaking, be what this guy looks like, as long as I didn't miss any of the edges. Now, fun fact. So this guy's different than the other examples where you were not originally given the Hosta diagram. But what you are given is this relation right here. So let's look at a couple of examples, and I'm really only going to look at a couple of examples here. So if you look at somebody who is a direct subset, so say we look at somebody like 1 and then 1, 3. Notice here, a direct subset, you totally get a chain. So what happens if you were looking at your meet and your join? So 1 and the meet of 1, 2, 3 would be the lower one. And if you did the join, it would be the upper one. And we're going to look at that relation here in just a second. Now, if we looked at a different pair, maybe you directly are on the same level. These guys are not subsets of each other. So if you look at 2, 3 and 2, 4, they're meet and join. Notice, though, when you go down, you're going to go down to the guy that's in common. So follow the little line, like I almost didn't. And the one in common here, the largest one in common is your 2. Now remember, these are really all sets. And when you look at the join, you go up and find the first one in common. So that would be this guy right here of the 2, 3, 4. Again, remember, they're really sets. And last pair of examples. So the last pair of examples is, suppose we have somebody like, oh, I don't know, how about those 2? So they look really crazy far away in the picture. So if we look at their meet and we look at their join, I don't want to do a 4 because that actually forms a chain. So instead of that one, we want somebody that doesn't form a chain. So how about 1, 3? So if we have 1, 3 and 1, 2, 4, the on purpose here was to get 2 different levels. And that didn't form a chain. So here, when you're traveling up, you've got to find the first place where these 2 guys, for the join, first place where you've got somebody that both of them are related to. Well, 1, 2, 3, 4, the first thing he's related to is the whole set. So that's got to be what the join is. Because 1, 3 was not related to 1, 2, 4. Now going down, maybe we won't have to go all the way down to the bottom of the post set. So here, when you start traveling down, you could get to 1, 2, 1, 4, or 2, 4. Okay, not super helpful so far. That misses 1, 3. And 1, 3, if you travel down, you can get either to 1 or to 3. Well, what happens when you're looking at these guys, maybe you travel down to 1, 2, and then you can travel down to 1. Well, that works all right. So I'm going to claim here that 1 is actually the meet. Why? Because if you go any higher up than this level of these one-element subsets, what happens, you'll get two-element subsets, and there's no common two-element subsets right here. Now, thinking in terms of sets, did anybody happen to know a relationship between our original sets and the answer sets for all of our meets and joins here? And I'm just going to go ahead and tell you, meets and joins here exist for everybody. So I'm going to claim for that first pair, this one right here, the chain, totally the same thing as an intersection versus a union. The question, of course, is that true for the rest of them? Well, it's true for the second one. What about for that last one? Is the intersection of the set 1, 3 and the set 1, 2, 3, is that intersection 1? The answer is, yeah, it actually is. It turns out if you have posets defined in this particular way, what happens? Your meet, so A meet B, is the same as A intersect B. A join B is the same as A union B. And that's one of the things you can start defining if you actually have a formula for your relation. You can do the same thing in our other common example, which is our D examples where we have our factors. I'm not going to write out this one, but here it turns out that if you look at your meet, it is going to end up being the GCD. Now, why would it be a GCD and not an intersection? Because here you're dealing with factors. So this would be the GCD of A and B. If you looked at your join, this would be the least common multiple of A and B. And I'll let you guys build this Hosta diagram and check to see if that actually works, or really pick anybody of this format with a different number, maybe something much smaller like we did in a previous class. Check to see if that actually works. But the last thing that I wanted to talk about today was actually a definition. And we're going to have time to give the definition, and it goes like this. It's really just a name. It's something called a boolean algebra, and it turns out we've already been dealing with them. They are all of those BN guys that we've been dealing with. That B actually stood for Boolean algebra. They are all defined the same way, where your building set is some power set, and then your relation is by way of set inclusion. So all of them are like that. Now, turns out those guys are always lattices. And here is the second big thing, and it is a fact. I don't remember what number it is in your textbook, but this is the tie-in between the Boolean algebras and these D guys, these divisor posets. It turns out if n equals a bunch of different primes, so when you do the prime factorization of the number n, you have to have all distinct primes. In other words, no primes raised to powers. Then, turns out, if you look at a poset that is D with a subscript that same n, this guy is a Boolean algebra, and I can even tell you which one it is. It's going to be isomorphic to the Boolean algebra BK, where K is the number of distinct primes you actually had. Okay? So, that being said, see if you can't answer the question that's up there on Poll Everywhere. Right? It is currently activated, and what it says is, can you tell if any of these D guys are also Boolean algebras? Okay? So see if you can't figure that guy out, but in terms of the last thing of Boolean algebras, really the only thing was saying that our BNs were considered Boolean algebras. Boolean algebras are always lattices, and it turns out our DNs are isomorphic to Boolean algebras, specifically depending on that prime factorization of that special number n that they're all defined off of. Let me do one example here for you. Specifically, D12. So here, you take the prime factorization. And if you have the prime factorization, notice because of that exponent, what would be our conclusion? This guy is not a Boolean algebra. And that's how to apply this guy. Okay. Just to make sure you're comfortable applying that theorem. Yes, because of that repeated 2. Now, compare and contrast. So let me go ahead and do one more example for us. Do my normal example color. If you have something like D15, the n here is 15, what's the prime factorization of 15? Don't overthink it. Anybody got the prime factorization of 15? Yep, this would be 3 times 5. Notice there's no repeated prime here. So this one tells us that you are a Boolean algebra. And in fact, I could tell you that D15 is isomorphic to one of the Boolean algebras. Anybody have a guess what that subscript is? Nope. So the subscript matches the number of distinct primes. So it won't ever be the actual n. Yep, it'll just be the 2. And if you actually drew out the Hosta diagram, it'd be really, really easy to see. So even if you didn't have that catch of directly who's it isomorphic to. But that right there is a really, really fast way of say, oh, hey, I'm dealing with either Boolean algebras or really more likely, you're dealing with these D posets and say, oh, and now I can do Boolean algebra stuff. Okay. Because the thing that we totally ran out of time on is that both lattices and then the special type of lattices called Boolean algebras have tons of properties that you get for free. And if you guys ever play around with gray codes, those guys are our Boolean algebras. So you guys will actually see Boolean algebras quite a bit typically when you start dealing with those things, if you haven't already. But that is me talking too much for you. Sorry about that. But that's it in terms of our topics. If you do run into any questions that you have, let me know. I'll hang out. Be happy to answer.